Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a stepped bar with linear static analysis. So in this stepped bar, we have two material. One is aluminium, another one is steel, another one is aluminium. So just see the graphical picture. So this is our case. So this one is steel, this one is aluminium. So here we are fixing it. This having cross section, this having length and breadth of 0.2 and 0.2, and this is having 0.1 and 0.1. So we are just going to apply 1000 Newton force axially. We are going to check the results with the analytical results. This is our case. In this case, the total deformation is equal to sum of the deformation in the first bar and deformation in the second bar. So the same thing we have calculated. So this is our case. So we are getting strain, we are getting displacement in first bar is displacement in steel is 1.19 E into 10 power minus 7, and displacement in meter, and displacement in aluminum is 1.42 into 10 power minus 6 meter. So this is the strain, and from that we have calculated the stresses. So stress on the steel is 25,000 Newton per meter square, and stress in the aluminum is 1 lakh meter per square, 1 into 10 power 5 Newton per meter square. So we will check these results. So here you can see this is the displacement plot, and this one is the von Mises stresses, and this one is the normal stress. So while doing this, a body having two materials, see, there are two bodies, one is steel, another one is aluminum. In between we need to specify the contact. So here we need to specify glue contact. So otherwise we can use merge nodes. Whatever the surface nodes in the steel, that has to be merged with the surface in the aluminum body. So one way is we can make a node merged on a same node. Another way is we can specify glue contact here. In this tutorial I am going to specify here a merge node concept. So let's get started. So I am just opening Salome meca. So just go to geometry model. In this tutorial I am going to model this in 3D element. The same thing we can do in 2D element and 1D element also. So first we'll see how in 3D element. So first go to new entity. Here also we can take it from the toolbar. Otherwise we can take it from the icon also. These icons, just create box. So check the dimension. So both are 1 meter actually, not total 1 meter. This is 1 meter and this one also 1 meter. So axis length is 1 and y and z direction are 0.2. So this one is 1 and this length is 0.2 and this length also 0.2. Just move this dialog box to left side and use this icon. This is a fit all icon, so I can fit it. This is panning. This is pan with fit. This option is for rotating. These are different kind of views. So this is my object, just apply it. My second object, my second volume, aluminum, is same one, length is 1 meter, but the cross section is 0.1 and 0.1. So similarly just create 1, this one is 0.1 and this one is 0.1, then apply and close. Now you can see this is the first box, This one is the second box. Now I just want to move this second body to here. So for that we are going to use the tool called translation. So make sure that you have clicked or you have selected this box to go to operation, go for transformation. The first option is called translation. Use this translation. Now I just want to move this into 1. So this is 1. It has moved here. Then I just want to move this into center of this body. So this one is 0.1 actually. For that I just want to move 0.05. Here also 0.05. You see? So now it has moved here. So if you want to create copy, means it will create one more object. No, I don't want to create a copy. I just want to translate this box too. For that you just untick this create copy and apply and close. Now you see this box 2 is translated to here. Okay. Now we can fuse. We can make body into single body. So before that we'll create one surface. So we'll see the surface will be used later. So I just created this mid surface between these two objects. Then now we'll go fuse this object. Select this box 1 and press Ctrl and Hold and select this box 2. Go to operation, boolean, make it fuse. Apply and close. Now this box 1 and box 2, the steel body and aluminum body, both become single body. If you want to know it, just go select this fuse one, go to explode. Here you can see only shell. If you can see solid here, that means that we can explode into solids. But you can make it only shell, that means that this is a single body. Now we just want to split this body into two body. For that we are going to use this surface. So the option we are going to use is partition. So choose this partition. So our object is fuse, tool object is this group 1. This is that's why I have selected. Based on this group 1 surface, we are going to split this body into 2. Just give apply and close. Now we have created this partition. Now just go to new entity, explode. Now you can see compound solid or solid. That means it has number of solids. Now just see solid, apply and close. Now this partition having two solids. Why we are creating like this way is, while creating a mesh, automatically we will get connected nodes. We need not to merge it. For that we need to do partition. So if you want to apply a glue contact separately, we need not to go for this one. We can directly take box 1 and box 2, we can do analysis. But to make a merged nodes here, we need to do partition. So now we have this one is the steel and this one is the aluminum. I just named. So these two body we have got, and we just want to create boundary groups for applying the fixed boundary condition and load boundary condition. Now just select this one, go here, group, create group, face. Now select the surface, add. This one is the fix, apply it. Similarly select this face, add. This one is the load, apply and close. Now for this body we need to specify different material property, and for this body we need to specify different material property. For that I have created two separate volume groups. Then the left side surface I just want to apply constraints to fix x, y and z directions, and the right side surface I just want to apply load. For that I have created groups. Now we can save this file. Go to file, save as, So I have already one more file here, that's why I am naming it 12. Now I have saved it. Now we can go for meshing. Just move into mesh, select this partition one, go for mesh, create mesh. Now we are going to use tetra element. For that, use NetGen 1D 2D 3D, simple parameters, use the local length 5. OK, apply and close. Right click, compute. Now you can see this is the mesh we have created, and here you can see the nodes are properly connected. So if you want to see mesh or elements inside the body, just right click here, go to clipping. Here just go to new, any absolute or relative. This is our plane. Somewhere you can move it. I'm just moving in the mid position because we just want to see how node is created here, or we can go by a plane also. This way or this way, this way. I'm just moving here to the mid. Not here. Little here. Now we can apply. Now just rotate it. You see? So this is the way the mesh is generated and nodes are properly connected. Nodes are properly connected here. This is the first body and second body. Now whatever the force we are applying, that will be transferred to this second body also. This is one of the way to apply to solve assembly models. The second way is we can apply contacts here. So if you want to apply a glue contact, we need to specify it master and slave surfaces to solve it. So I'm just untinting here. If you want to delete it, we can delete it, close it. Now go to clipping, apply, just close. Now see, it has reverted back. So now we have got the mesh. Now we just check the groups. Steel body is a volume group, aluminum is the volume group, and fixing the left side is a node group, elemental group. Load, here we are going to apply the load. Now we can save this file. Now we have done geometry modeling and meshing. Now we can move into code aster, that means aster study. So I'm just choosing stable. Now we have done modeling. Now we just want to apply boundary condition, load, and defining the problem. So now to assembly analysis, just right click here, add stages. So we just want to add stage one by one. First we need to read the mesh. Read mesh, choose mesh 1. It has got MED is the format. Apply. This is the command it will generate at the back. Just say OK. Now we have read the mesh. Go to model. First we need to specify the model. Finite element model. This is, we can specify everywhere. Mechanic 3D model. Say OK, apply and close. Now we define the model. We need not to specify this one because we are not simplifying the case 3D into beam element or shell element. If you are using a beam element or shell element, we need to use this one, otherwise not required. Now we move into material. Now first we need to define the material. We have two materials, so we need to define one by one. First material is steel. So Young's modulus is 210 e power 9 and Poisson ratio is 0.3. Make it okay. So just apply it, save okay. The first material we have done. Again we just want to click it, define material. So this one is aluminum. I just giving AL. Again linear isotropic material. So this one is 70 gigapascal, 70 into e power 9 and Poisson ratio is 0.33. Okay, just apply, save okay. Now we have created a steel material, we have created the aluminum material. Then we just want to assign the material to the body. Just go to assign material. Just keep this name, make it mesh, make it model. Just tick this mesh and model. Now go, just make it 2 because we need to assign 2 material. Not everywhere. So if you have only one body, we can go for everyone, we can apply it. Now we have 2 bodies. We just want to use group elements, edit. First one is steel. Choose the steel, save OK. Define here, choose the steel, save OK. The second one, you just go here, group of elements, make it aluminum, save OK. Here choose, you just click it here and choose the aluminum here and save OK. Now we have defined mesh model and we have assigned the material property to this mesh, save OK. Now we have done material property. Functions, we are not applying any functions to in the load conditions, so just leave this one. Now just go to boundary conditions. We need to assign mechanical load. So load, so first one is we need to fix it, enforce degree of freedom, or we can go for phase impose. I'm just going to show how to use phase impose. Edit, group of element, edit, fix it. This one I just want to choose it, say OK. Only 3 degree of freedom. So for solid element, it's so this rotational degree of freedom need not to arrest because the solid element node having only 3 translation degree of freedom. This is enough to fix. Okay, save OK. So I have fixed here. Previously we have used how to use enforce degree of freedom. Now we are using phase impose. Now what we just want to do, we just want to apply force here. For that, just scroll down here. So these things are constraints, these are contacts and other solid connections. These are connections, liaisons or connections. Here we can see force nodal, force phase, force edge. So now we can go for force phase, select this one, edit. First choose the load. Here we just want to apply, save OK. Force in x direction. Here what we just want to do is this command, this force phase command, always apply as a pressure. So what it will do is there is no force which is applying in a point. So every force having some phases, some area. So this also will apply in some area. So our area here is, see, this is 0.1 and 0.1, that means area is 0.01. So here, that is we need to define it. Only real number only we can enter it. You can see here, other any variable we need to go with variable, click it here. So I just want to apply as a force, expression we can give it. So 1000 is the force divided by area 0.01. So this is the value to apply. Now just apply, close. Now this force variable will came here. So that will came here. Now this is the load, save OK, then apply, save OK. Now we have in boundary condition loads, we have fixed left side and we have applied force here. So the variable command is came here. It's simple variable. So it will read the Python command like simply force is equal to 1000 by area. This is the load it will apply. So now we have done boundary conditions. Now we choose pre-analysis. We need not to do any pre-analysis here. Move into analysis. Here static. Go to static. This is a linear static solver. Choose this linear static solver. If you want to rename it, you can rename it. I'm just keeping this old file name. In solver, we need to specify everything. We need to specify material. There is no structural element. We need to specify the model. We need to specify the loads. This only one loads. Just say OK. There is no time, step in times, everything. Then say apply. Say OK. Now we have specified the solver. Then you just go for post processing, because the primary variable displacement is the only variable it will calculate this solver. To the secondary variables like stress, strain, normal stresses, von Mises stress, everything we need to calculate from the displacement. For that you just go for post processing, call champ. This is unnamed. You have to name. You have to give some name. I'm just giving the same name. Same name. Go to constraint. Here we can choose directional stresses. Sigma element and sigma node. What it will be is directional stresses. That means sigma xx, sigma yy, sigma zz and sigma xy. That values will calculate from this command. Deformation means strain values. So we are going to see strain now. I'm just going to check with the criteria. That means von Mises stresses. That is sigma equivalent. No means element and nodes. These things we needed, we required. So I just chosen result, model, material. Remaining we need not to specify anything. Just apply it. Say OK. Now we have calculated stresses, von Mises stresses, principal stresses, everything. Now we can save these values. For that, set output results. Just go here, just click this one, save this file in merge nodes. For already we have this result file, that's why I'm just naming as result12.rmed. This is the file format. So this is the file format. Paraview will read. Just save. Now just go for add. Just edit. Here we just want to include this one. Here don't choose meca static because we have derived the value. So for that you just use this call champ. Then you just go for that. One more option is called tau champ. You just tick this one, make it yes. This is enough. Otherwise we can go for norm champ. One by one we need to specify it to extract. So whatever value it's calculating, that all the values it will save. That is the command called tau champ, make it yes. So just go to OK. Here you just make a format as med, then apply, save OK. Now we have done setup. All the setup we have done. Now we can go for solving. So just save this file. Go to history view. Here you just first click this one. Next you just click this one. Make this one into 5 seconds. Then run it. Just wait for a while, it will solve. If any error comes, it will come as a red color. That means some error is coming. So now you can see there is no error. Diagnostic job is okay. So no error. So it will update later on. Yes. Now see, green color with tick means there is no error. It is solved nicely. So it is reading command file. You can see here whatever we are doing is one by one it's reading. So it's input. So reading the mesh. It's taking the model. So material, everything, it's one by one it will read and it solves. Here you see it solves the equations this much. So how it is getting solving, everything is coming. Now we can go for post processing in Paraview. So I'm just saving here. Go here, Paraview. Just right click this built-in, open. Go to pictures, code aster, bonded content, merge nodes. Result12 RMD is the current file. Just select this file. So these are the results it's saving. Displacement, equivalent stresses, that means von Mises stresses, principal stresses, Tresca stresses, everything it will calculate in SI, EQ, no. And this one is the normal stresses. So just apply it. Now we have model. Now go to solid color, displacement. So to change this color pattern, I'm just going down here. Click it here. Just go to rainbow. Apply and close. Then again you just make it this into 12. So now this is the displacement. This is actually displacement magnitude. If you want to see displacement in direction, in x direction, because this is axially loaded bar, we are just pulling in this right side. We are fixing here. So this is the displacement. So here you can compare the results. Just go here. So delta 2 is the red one, is 1.4 e power 10 power minus 6. Now see, this aluminum deformation is 1.5 into 10 power minus 6. So almost very closer answer we are getting in finite element analysis. If you want to check the displacement in this body only, so we can mask. So for that, what we can do, so any view we can set. This view I'm setting it. Here there is a different options, you can see it. This one is see, select the cells, just click this one, make a small box and select it. Now I have selected it. Now what we can do is just go to filters, search here, type extract. So what it will do, extract commands, all the extract command will come. There is an option called extract selection. Select this one, press enter. So these are the elements we have selected. This only it will show. Apply. Now see, only the elements whatever we have extracted, that only it's showing. Now we just want to see the results here. For that, just scroll down here. In this pattern there are different icon is there. One is rescale to this custom range. We can scale whatever the scale is there is, that is we can rescale what by manually by giving input. Then second one is called rescale to data range over all time states. Third one is rescale to the visible range. That means whatever the value here is there, that will be rescaled to this one. So that one we need to select. Just click this one. So this is rescale to visible range. So this is the maximum value of 1.3 into 10 power minus 7. So this is the maximum values coming in the steel. Just go to the model, here. So 1.1 into 10 power minus 7 we are getting in analytically. Here 1.3 into 10 power minus 7. So here also we are getting the very close value. So similarly we can check with the stress also. Go for sigma. Here just make it to sigma x axis. So here also you just make a rescale it, and you just scroll down here, make it 12 and make this into blue to red. Apply, close. So the stress we are getting here is, so this is because there is sudden change in the cross section, that's why we are getting sudden stresses. So this is, we need to hide it. For that, what we just want to do, from this we will select only here. This is the stress we just want to say. So here we are applying constraint, we need to avoid this also. Here also we need to avoid. So what I'm going to do is same. I'm setting this view, only this one I'm going to take. So element, only this. I'm just removing this previous selection. Now what I'm going to do is same element, this one I'm going to take, go to filters, search, extract, selection, enter it, just apply it. So this is the body. Sorry, this is only select this surface elements. If you want to select all the volume elements, you need to go with this, select this one, it will select all the elements inside the box. Go to filter, search, extract, selection, enter, just apply it. Now we have got the volume element. Now just go for 1v stresses, make to rescale it. Now see what stress we are getting. Just compare with this yellow color. So this is around 24,000. What we are getting? 25,000. To exactly, if you want to know, there is a point, question mark with the point. Just select this one, place it here. Now you just here in this dialog box, you can see it in the SI wrestling underscore sigma node, the first value 25,000. That is the value we need to check. So we are getting exact value, actually 25,000 is the value. Von Mises stress also you can see, that means wrestling SIEQ node, the first value is the Von Mises stress. So 25,000 is the Von Mises stress also. So whatever analytically we are getting, the same value we are getting in the steel. Similarly, we can check with the, I'm just coming out from this one, we can check with the aluminum also. So aluminum, you just avoiding taking elements here and here, because here we are applying the force load. Here we are giving, there is sudden change, so due to that the stress will come more. So whatever analytically we are calculating is away from the boundary conditions. So just make it here. I'm just selecting the element only away from the boundary conditions. Go to filters, search, extract, selection, press enter, apply it. Now we have this one. Now just go here, rescale this range. Now we can check the stress. Now you can see the red color, 1 e power 5. Here what we are getting, 1 e power 5. The same value we are getting. So exact value we are getting. So this is the way we can compare. If you want to if you want to add more elements, so what we can do is, here there is an option, you just go up, there is an option called plus button, grow selection. This is, we have selected elements. If you want to add elements, just select this, copy active selection, apply it. Now see, it is getting growing. Again, you just press it, copy active selection, apply it. Now we can, if you, example, somewhere we are getting very high stress, from that if you want to check the results, means this way we can use it. Just press this one, copy selection, apply it. So this way, see here the stress is changing because here we are applying the load. Due to that, the stress getting distortion. So this is the way we can compare the result and check the results in Paraview. So to go for full width, just make this one. So to unselect all the elements, just this one, just go to equivalent. So this way. So and to view the deformed shape, we just go for a wrap Y vector, then we just make it some scale, apply it. So this is the way it will get deformed. To animate it, just right click here, create animation, just give some 20 frames, say OK. Now we can animate it. So the aluminum having less stiffness, that's why the deformation is high, and the steel having more stiffness. So whatever the load we are applying, most of the load is taken by the aluminum, very less load is given to this. The steel taking the low stress of, just here you can see in our calculation. So the steel getting stress of 25,000, but the aluminum getting stress of 1 E/5. So in this tutorial we have learned how to solve assembly model with partition contact, that means merge nodes. In next tutorial we will see how to use glue contact pair using Salome meca, and we have learned how to see the results in Paraview. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.